All right, in this segment, we're going to be taking a step further. Last segment, we talked about relating the standard potential to the standard free energy. But of course, many times the concentrations or the situations are not in standard state. So in this segment, we're going to calculate the cell potential at non-standard conditions and explain how a concentration cell works and calculate the cell potential in a concentration cell. All right, so cell potential under non-standard conditions. So we know that the free energy is going to be equal to the standard state free energy plus RT ln Q. And then we can just plug in the same way that we define the free energy of a standard state as minus n Faraday's constant times the cell standard state energy. The free energy is minus n times Faraday constant times the potential energy of the cell, regardless of whether it's standard state or not. Okay, so you just plug in that for the free energy. And then you can rearrange, just divide by minus NFE and get that the potential of the cell is equal to the standard potential of the cell minus RT divided by N times the Faraday constant times the log of Q. So this is the Nernst equation, and it can help us determine the cell potential at non-standard conditions. For example, frequently your acid is not going to be pH 0. It'll be less strong, and so the cell potential will change in this situation. So because of this, if you have different concentrations, for example, in a standard cell, we can calculate the voltage just by taking the 0.76 and adding it to the 0.34, we get a 1.10 volt. But if we lower the concentration of the zinc and raise the concentration of the copper, it turns out we actually get a little bit of a higher voltage. So what's going on here? So so we could just plug it into the Nernst equation and you get exactly that relationship. But here, notice that the zinc is lower than standard concentration. And we know that it goes in the direction of oxidation of zinc. In other words, production of zinc 2 plus ions. So if the concentration is lower, there's going to be a driving force to reach equilibrium by putting more zinc into solution. So that will make the reaction more spontaneous, which means that we can get more energy out of it. The cell potential will be larger. Same with the copper 2 plus. Remember, the copper wants to leave solution and plate the copper cathode. And therefore, if you have more than the standard potential, that will also be driving it towards being more spontaneous because it'll want to get rid of that concentration. Obviously, if you made the zinc higher than 1 molar and the copper less than 1 molar, then it would be more like 1.03. It would become less spontaneous. You could get less energy out of it. So that's how concentration affects a cell. So specifically a concentration cell by itself, it's possible to get a spontaneous reaction where the oxidation and reduction reactions are exactly the same as long as the electrolyte concentrations are different. So you plug that into the Nernst equation, and in that case, of course, because it's the same oxidation and reduction happening, then E standard state is 0. But you can still have a cell potential because you still got the minus RT over NF log Q there. So electrons will flow from the electrode in the less concentrated solution to the electrode in the more concentrated solution. Oxidation of the electrode in the less concentrated solution will increase the ion concentration of the solution. The less concentrated solution has the anode, and the reduction of the solution ion at the electrode in the more concentrated solution reduces the ion concentration. Therefore, the more concentrated solution has the anode. Depending on where the concentration is higher, that will determine the direction the electrons flow, and the electrons will flow. The electrons will flow from the less concentrated solution because if they leave the less concentrated solution, they will put more ions in there and they'll flow to the more concentrated solution because electrons there will pull ions out of the system. Okay, so let's do a couple of examples. The first one will just be a standard cell whose potential will change because of the concentration. So then we'll look at one that actually is a concentration cell that only depends on, where the potential only depends on the change in concentrations. Okay, so we want to determine the cell potential for an electrochemical cell based on the following two half reactions: oxidation of copper and reduction of manganate to magnesium oxide. So the first thing we need to do, what's the equation that we'll be using? We'll be using the equation that the E cell, that's what we need to calculate, is going to be the standard state cell minus RT over NF times log Q. And so in this case, we can get E standard state for cell. So let's look at the chart. So copper reduction is 0.34, and then we're looking at manganese going to magnesium oxide to the +4 state has 1.68. So that reduction really wants to happen. That is the reduction, okay, and 0.34. So let's go back to the problem. And so the copper reduction is 0.34. So for the reaction written here, which is the oxidation, the E oxidation will be minus 0.34, and this will be E reduction is 1.68. So the E cell, a standard for the cell, these are standard states, will be 1.68 minus 0.34. So that will equal 1.34. So that's the standard standard potential for the cell. Okay, so that gives us this part. Then what we need to do is we need to figure out Q. So for Q, we need to figure out the overall reaction. So let's write out the reactions. The oxidation is Cu solid goes to Cu2 plus aqueous plus 2 electrons, and the reduction is MnO4 minus aqueous. And I'm writing out the phases because we're going to be doing, writing out an equilibrium expression. So we got to remember the phases. Plus 3 electrons goes to MnO2 solid plus 2 H2O liquid. Okay, so notice we don't have the same number of electrons being transferred, so we're going to have to multiply. Let's multiply this by 3 to get 6 electrons here, and multiply this by 2. So this becomes 8. That'll become 8, and this will become 6. And that'll be 2, and that'll be 4. So this is 8, this is 6, this is 2, and this is 4. Great. Okay, so then what we do is we add them together to get the overall reaction. We get 3Cu solid plus 2 MnO4 minus Aq plus AH plus AQ plus, now the electrons cancel out, so we get that this goes to 2 MnO2 solid plus 4 H2O liquid plus 3 Cu2 plus AQ. So that's the total reaction. So let's write out the expression for the reaction quotient, and that is going to be on the product side, we just have Cu2 plus, and that's going to be cubed. We got solid and liquid there, so those aren't included. And this side, for the reactant side, we have MnO4 minus squared and H plus to the 8. Okay, and that is all the species that are involved there. So now we can take a look. We can actually plug those in. So Q is going to be equal. The copper concentration is 0.01 cubed. This is 2.0. And then the acid is at, so that's 2.0 squared. And the acid is at 1.0 to the 8th, nicely. So that ends up being 2.5 times 10 to the negative 7. So that's Q. So now let's plug this in. So E cell is equal to 1.34 minus, let's assume it's at 298, and K times 8.314 joules per mole Kelvin. Kelvins cancel. We have 6 moles of electrons transferred. Like that's, we have to be careful when we look at the half reaction, so we know how many moles of electrons are transferred, divided by 96,485 coulombs per mole. And so the moles cancel. And so our answer will be in joules per coulomb, which is correct. That's going to be in volts. So 1.34, we multiply this all together. This is 0.00428 volts, because it's joules per coulomb, times the logarithm of this, which is minus 15.2, for a total of 1.34. And that's minus here, minus there, plus 0.065. So that rounds to 1.40 volts. So the concentrations here are such that we get a little bit more potential out, a little bit more electrical potential out than we would have at standard state conditions. So what would change this the most? Well, we've got the acid concentration being quite high. This is pH of 0. So we have a very high concentration of hydronium. What would happen if we drop that to say pH of even 2? Well, in that case, in the denominator, we'd get 10 to the minus 2 to the 18th to the 16th. So this would push this, instead of being 2.5 times 10 to the minus 7th, it would push it to being like 2.5 times 10 to the 9th. And so all of a sudden, something that was contributing 0.065 to the voltage would be lessening the voltage by, maybe 0.1 or so. So if this was in less acidic conditions, that would substantially decrease the cell potential. And so you can see how those sorts of conditions, can affect things significantly, especially in this case because there's such a high exponent on the acid here. A small change in acid, from pH 0 to pH 2 could make a big difference.